Is a demo of the tool booklet. Oh, this is tricky actually. Yeah, we've got two separate windows. Can you do it with browser? Can you screen mirroring instead, or maybe it'll just rotate? Sorry, guys. Awesome. Okay, so this is the landing page for the Climate Adapted Seed Tool. You can find it at reforestationtools.org. And if we click on Launch Cast, it's going to take us into the tool. So we've got the tool right here. It's set up to have sensible defaults, things that we can change. So it's currently optimized find seeds for the climate about 20 years in the future. And then different keyword settings. If we click on the map, we can select a planting location. It's doing some calculations in the background. And it's going to show us a map of potential seed sources. These are by seed zone and elevation band. So it always puts the local seed zone. These are the tree seed zones for California at the top of the list. You can see here it's estimating that we'll get a 24% decline in productivity for the local seed source. Versus if we shift to a seed source from a bit of a lower elevation, we can get closer to about a 0% decline in productivity for that seed source. Has similar functionality to the last tool we looked at, where we can either find a seed source or find planting sites specific to our area. And then it's also estimating carbon sequestration. If you hover over there, there'll be units for it. So the units in this is tons, at age 80 in metric tons per acre. We can adjust the age on that. These growth and yield functions are fit to FIA data, and then the transfer functions are fit to common garden data. We can adjust our maximum geographic transfer distance. We can select different additional variables. If we want to look at lumber produced, I think this is in board feet per acre maybe, but we hover over there. So yeah, just wanted to start off by giving you guys a quick tour of the tool. Oh, and by the way, so current availability is in 5 western states. We only have the seed zones. And then there's a version unreleased on the website, but the link is not hard to find, that actually has the LAMRC inventory built into it. So you can see specific seed lots that are in the inventory there as well. So the only functionality outside of California right now is just to view and download the rasters as opposed to integrating the seed zones. Cool. We'll switch back to PowerPoint. Can we just share all windows in case I want to switch back again? Desktop. I think we just, Awesome. So I'm just going to talk about some analyses underlying the tool. So we know from large amounts of common garden data sets, we're working with common garden data sets from Western North America spanning 15 different species and about 350,000 trees planted in those common gardens across Western North America. Unfortunately, mostly from up in British Columbia, but scattered throughout the states as well. The tree populations tend to be adapted to the historical climate that they're found in. So we've got on the x-axis here is transfer distance for mean annual temperature. So this is site climate minus seed source climate. And then we've got relative volume factor. And then this black line is just a rolling mean. Incidentally, you don't need any fancy statistics to see that this is the case. You can just look at this demonstration provenance test, planted in Greg O'Neill's yard in front of his office up in British Columbia, where you see that the height of these trees is analogous to the right-hand side of this rolling mean going through the data. And if we fit multi-dimensional climate transfer functions, this is a three-dimensional representation of a multi-dimensional climate transfer function, we can use those to predict what's likely to happen in California to local seed sources in absence of climate-adapted seed transfer. So you can see, not everywhere, but large portions of California are projected to suffer pretty substantial declines in productivity. In some locations, in excess of 50% decline in productivity for local seed sources in the absence of moving seeds around. But that represents both a crisis and an opportunity, because in areas that we're already doing reforestation, the simple intervention of switching up the seed source can lead to much better outcomes. This is estimates just for private land, because it's easier to estimate the actual amount of reforestation happening on private land. This is assuming a 60-year rotation cycle, which is probably a little bit too conservative, so these are probably underestimates. But I think just to highlight the point that just if we switch from local seed sources to climate-adapted seed sources, within the next 30 years, on an annual basis, this solution alone can sequester 1% of California's net greenhouse gas emissions. And of course, that's going to be larger in states like Oregon or Washington, where tree productivity is higher relative to population levels. Of course, we face a trade-off with assisted gene flow. The climate-adapted seed tool currently defaults to optimizing for climate conditions about 20 years in the future. But the trade-off there is that we're planting them into climates that are initially a little bit too cold. Some early data from Emily Moran, where she's analyzing seed lots selected for 20 years in the future, is actually showing that these ones are doing the best currently under the first 5 years of growth. I forget the exact detail. But then, of course, the trade-off is that if we're optimizing for 20 years into the future, for the rest of the tree's lifetime, and depending on what we're planting these trees for, whether it's for timber production or for restoration of ecosystems that we want to grow into old growth forests, maybe they're growing in environments that are too hot for them. Unless we rein in and reverse climate change, then I don't know. Uncertainty in what's going to happen in the future. So yeah, this is just locations of common garden sites. So 15 species that we're working with, locations that are planted. You can see most of them up in British Columbia, with less data down in California. One site in Arizona. I think that one is one of the ones that's grown for close to 100 years. But if you look at the seed sources, which is, you can argue which one's more relevant using these transfer functions in particular areas. We've got a better density of seed sources that come from the United States and from California. Incidentally, these are a lot of single tree collections for Kilo, Corpus Lomota right there. So kind of inflates the numbers there. This is just another view of the data set. So these are number of trees measured over time for various field ages for 15 different species that we're looking at. So let's see. Douglas fir, we've got measurements up to almost 100 years old, but most of these species, the experiments stop around 20, 30 years. In some cases, they've only run for a much shorter number of years. I think in one case, only up to 3 years, maybe up to 10 years. So we've got a paucity of data extending beyond 30 years. And what happens beyond that point, I don't know if we can really answer. I've tried to analyze the sparse data that we have that goes out past that time, but it's a mystery to me, right? Do all the effects of climate adaptation happen in the first 30 years, and then there isn't much of an effect, or that you continue to get progressive effects at older ages? Time will tell if these experiments stay on the ground and we can continue measuring them. A big operating assumption behind the climate adapted seed tool, I think this is useful given that we've got data for some species and it's sort of erratic what the measurement gauges are and where it's located, is that there tends to be more commonality than difference in climate transfer functions. So built into the tool currently are transfer functions fit to common garden data for 2 species, and we're working on expanding that. That's lodgepole pine, which is the default stand-in for all the other species. It's one of the most robust data sets, and then Douglas fir. And so this is just one way of sort of comparing these different data sets. These are climate transfer functions, asymmetric bell-shaped curves for mean annual temperature. And then this is the decline in productivity associated with 3 degrees Celsius transfer difference. And you can see there are some species that differ and don't overlap. But for the most part, there's a lot of overlap between these declines in productivities, these sensitivities to climate change. So another thing we're working on is a portfolio reliability optimizer approach within the climate adapted seed tool. And the philosophy behind this is that the same level of like analytical detail that goes into diversification for financial assets, so like your retirement portfolio, should go into selecting seeds for reforestation sites. So I mean, this is essentially just a figure that I saw. I think it was on Personal Capital, right? Like where it's got this like little slider where it says like your portfolio is about here. You might be able to get higher returns by this portfolio, but you might be able to get more reliable returns here. So this is the Pareto optimum. This is based off of real provenance test data and some early simple assumptions. We've got a preliminary version of the tool, which I could show you. I'm not sure if we'll have time right now, right? But so we've simulated, I don't know, 10,000 different, just random combinations of different portfolios here. Different distributions of future climate fit to asymmetric multivariate distributions fit to future global circulation models. And we're also factoring in the uncertainty associated with the models themselves and working on spatial autocorrelation and sampling error, so accounting for like the number of trees that you're planting, because that affects reliability as well right here. So less risky, but a little bit lower expected return. But you can see that just by switching between portfolio composed of a single tree to a portfolio composed of a single seed source to a portfolio composed of 2 seed sources, or up to 3 seed sources, you can get pretty substantial declines in uncertainty of what the outcome is going to be for that seed source, with pretty minimal cost in terms of your expected mean relative productivity overall. What am I doing on time?
We've got 3 minutes.
Okay. This is just like try to think through what the most sensible way is to portray this information in a tool is. I think from what I've read, quantiles are much easier for people to grasp in general. So this is like the worst case or unfavorable outcome. If instead of putting the standard deviation on one axis, we put a 10% quantile on one axis, that might be a conceptually better way to present this information to managers. I mean, this is a really tricky thing. I'm not sure really how to handle. Right? So we can use the range of global circulation model outputs at a particular location to construct probability distributions for what the future climate's going to be at a site. But in terms of assigning probabilities to what the emission scenario is, that's sort of tricky. I've played around with it a little bit. I think like somewhere in the mid to upper range, it seems to be on the more likely side. And like maybe we want to have the ability for users to like edit this, like assign different relative probabilities to the emission scenarios. Certainly want to have a default in there. Maybe the default that makes the most sense is just equal probabilities for each of these emission scenarios. If anybody has ideas or knows people who are working on, I don't know, I think sea level rise folks are thinking about this a lot, how to assign probabilities to these things. If anybody can connect me with people who are thinking about that, that'd be useful. So yeah, that's just a multivariate version of looking at those future climate scenarios. Another source of uncertainty, for a lot of the seed lots in the inventory, Forest Service or the CAL FIRE inventories, we can narrow it down to much more precise locations the seeds came from through PLSS, township section range. But this legacy system of seed zones and elevation bands, I was hearing that seed zones are new age for like forbs and like smaller things for trees. This map was built in 1970. Before we had good climate data. And so some of these seed zones have about 6 degrees Celsius mean annual temperature geographic distance between one location in the seed zone and another location in the seed zone. My general opinion, right, like, is we should be using precise information as much as possible. Seed zones are useful for binning things into different categories and maybe creating rules to protect uncareful or not bad actors from transferring things too far. But if we want to optimize things, we want to get rid of geographic uncertainty as much as possible and use precise locations. Model uncertainty is, of course, another source of uncertainty, right? Like, the models do a great job of predicting the mean outcome, but there's lots of noise above and below that. Granted, that noise is much lower once you're accounting for multiple dimensions of climate change at once, as opposed to just single dimensions of climate change. Distance between seed source and spatial autocorrelation. So the current version of the diversified portfolio tool that we have right now, if two seed sources are right next to each other, it doesn't make any assumptions about their variance being greater or less. But what we can see from looking at the residual semi-variance is that seed sources that are further apart have larger variance, so you're going to get more reduction in uncertainty by using two seed sources that are further apart, all else being equal. And this is sort of just, this makes sense, right? Like most of the common garden experiments have somewhere in the vicinity of about 20 provenance trees from a particular provenance at each site, right? But in one case, big leaf maple, we've got some common gardens that have much higher numbers of trees, and we can see that our root mean squared error goes way down if we use the entire data set for all the trees in there versus just subsampling a smaller number of those trees. So there's a fair amount of measurement error that's built into these data sets. Also working on climate-adapted seed collection prioritization. So the approach here is to create a probabilistic framework for where reforestation is likely to be needed on the landscape in the future. This just assumes 1% probability, I think, per year across the landscape for ponderosa pine. And then relative to the existing inventory, if seed is collected at a particular location, I wanted to put this in like a unit that makes sense. What is the gain in carbon sequestration that we can get from collecting that seed source? And so the idea there is that you collect seed from that particular location, and you're calculating the probability that it might be useful in any number of possible deployment locations. And this is a marginal benefit because the first seed you collect is going to have the most benefit, and then as you collect more of that seed, you're starting to swamp out those most beneficial locations where it's likely to be planted. So this is the marginal gain in carbon dioxide sequestered in tons of carbon dioxide per pound of seed collected. So you can see certain locations in the distribution, at least according to this analysis, we're getting about 450 tons of carbon dioxide benefit per pound of seed collected, which I'm not sure if I have the math in front of me, but it works out to in the millions of dollars worth of carbon dioxide sequestered just for collecting 100 pounds of seed. So it shows the benefit of collecting in particular locations. And oftentimes these are sub-seed zone locations. So this is one seed zone, and this is just meant to illustrate these locations in the seed zone, not elevation band, not so much benefit. This location in the seed zone elevation band, huge benefit. That's what I got.